All right, guys, we're here to review the AMC 12B from 2023. Question one. We have orange juice in 4 glasses. 3 glasses are full, and 1 glass is 1/3 full. If we want to pour juice from the full glasses into the not full glass so that all 4 glasses have the same amount, how much should we pour? Okay, so we have 3 full plus another third. That's a total of 10 thirds of juice, 10 thirds cups of juice. And we're going to divide that into 4 glasses equally. So in the end, each glass should be 5/6 full. And that means we have to pour 1/6 from the full glass into the not full glass. Running shoes are on sale, 20% off each pair, but then we have to add sales tax. Carlos has $43. What's the original price of the most expensive shoe he could afford to buy? So if X is that price, first we're gonna decrease it by 20%, and then we're gonna add sales tax, and that should be 43. So it's interesting choice of numbers here, but it all works out, right? 4 times 1.075 is going to be 4 plus 0.3, right? 75 times 2 is 150, and times 2 again is 300. So what we have here is that X times 4.3 equals 5 times 43. And so X is going to be 10 times 5. Okay, we have a 3, 4, 5 right triangle inscribed inside one circle. So 3, 4, 5 inscribed means that the diameter of the first circle is 5. And 5, 12, 13 is another right triangle. And so 13 is the diameter of the second circle. The ratio of areas will be the square of the ratio of diameters. Jackson's paintbrush makes a strip with a given width, and he has enough paint to make a 25-meter long strip. How many square centimeters will that cover? Well, so 25 meters is 2,500 centimeters, and 6.5 millimeters is 0.65 centimeters. So this is the area. And let's see, if we multiply one number by 100 and divide the other number by 100, we're going to get 25 times 65 square centimeters. And now looking at the options, the only question is where to put the decimal. And we can see this one should have 5 as a units digit and no decimal. So it's got to be C. Maddie and Lara see a list of numbers on a blackboard. Maddie adds 3 to each number in the list and finds that the sum of her new numbers is 45. So I'm going to say that the sum, the original sum, plus 3 for each number in the list, let's say they're n numbers, is going to be 45. Lara multiplies each number by 3 and then finds a sum that's also 45. So that means 3 times the original sum is also 45. How many numbers are on the blackboard? Okay, system of equations, and it looks like I want to multiply the first equation by 3 and then subtract. And so I'll get 9n equals 3 times 45 minus 45. That gives me 2 times 45. And so n should be 10. Okay, L is 1, L1 is 1, L2 is 3, and then L follows a Fibonacci type sequence. How many terms in the sequence are even? Let's investigate the pattern. We go 1, 3, 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, 18, 29. And we can see that we're going to get an even number. We're never going to get consecutive even numbers, but we're going to get an even number after 2 odd numbers in a row. So, so it looks like every time that n is a multiple of 3, ln is going to be even. So how many multiples of 3 are there? Less than or equal to 2023. 2022 is the multiple of 3. And this should be, let's see, 6, 7, 4. 6, 7, 4. We have a square rotated. This picture a little bit bigger because angle A is pretty small. Rotated 20 degrees clockwise, and so we have a rotated square. What is the degree measure of EAB, the marked angle? So if it's rotated 20 degrees, that would be this angle, it's 20. It's a square, so that's a right angle. And that means that this angle here is 70. And by symmetry, this is an isosceles triangle. So, angle, so how do I say it? The complementary angle is 110, and so the marked angle is half of 70. It's 35 degrees. What is the units digit of this number? So if we only care about the units digit, then we actually don't care about any of that. And so this is a familiar kind of problem. We can find a recurrence. You can find a cyclic pattern in the units digit of a number raised to a power. So 2 raised to the first power is 2, and then 4, and then 8, and then 16, but we only care about the 6. And so 2 raised to the 5th power, right, is 32. And so anytime we have a multiple of 4, we're going to have 6 as a units digit. 2023 is one less than a multiple of 4, so we'll have 8 as a units digit. And then we'll do the same thing for the other number. We have 3 squared is 9, and then 27, and then 1, and then it goes back to 3. So again, it's a cycle of 4. 2022 is 2 less than a multiple of 4, so we're going to have 9 for the units digit. So add them together, and we'll have 7 for the units digit. 16 and 25 are consecutive positive perfect squares whose difference is 9. How many pairs of consecutive positive perfect squares have a difference less than or equal to 2023? Well, you might know this fact that the squares form a pattern. Like every pair of consecutive positive perfect squares, it has an odd difference. And in fact, has a unique odd number, right? So the difference 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16, 16 plus 9 is 25, and so on. And so each odd number between 3 and 2023 is associated with a pair of consecutive positive perfect squares. So basically, we're just asking how many odd numbers are there. So this is 2n plus 1, where n starts at 1 and goes up to 1, 0, 1, 1, right? 2, 0, 2, 2 plus 1. So, okay. So it looks like B is the answer. All right, we're playing a game. We have a 2x1 rectangle covering 2 squares of a 3x3 square of grids. We're not told which 2 squares are covered. We want to find at least one square that is covered by the rectangle. My turn is guessing a square, and we're told whether that square is covered or not. What's the minimum number of turns you need to ensure at least one of your guessed squares is covered? So basically, we need to cover squares and not have any 2x1 shape left uncovered. And so I can do that with these 4. So the answer is either 4 or fewer. Is it possible the answer is 3? I don't think so, because the only way to avoid having 2 in a row is to choose the middle one in that row. or to choose more, I have to have at least one in each row. And so it has to be the middle one. But if I choose the middle one in each row, that leaves plenty of room for my domino. So 3 is impossible. All right, we have $800 using 20, 50, and $100 bills. How many different collections of bills are possible? We have at least one of each. Well, one thing we realize is that 800 is an even number of 20s, and so is 20, and so is 100. But 50 is an even number of 10s, but 50 is an odd number of 10s. And so we have to have an even number of 50s no matter what. And so I think that if we have at least one of each, we can just subtract that amount. I have to have at least 100. I have to have at least two 50s and at least 120. So 800 minus 200 is 600 minus 20. So I have $580. And now there's no more restriction of needing at least one of each. So the number of hundreds is either 0, 1, 2, 3, 4, or 5. And now I think for each potential number of hundreds, I can count how many different possible numbers of 50s I can have. Right. So if I have 500s, I have only $80 left, and so I can't have any 50s. So there's only one way to choose the number of 50s that I have. On the other hand, if I have 400s, then I have 180 left. I can have either 0 or two $50 bills. Can't have 1 or 3, because then I can't make an odd number of 10s with 20s. And I can't have 4, because I only have $180 left. So there's 2 ways to do it, 0 or 2. And you can walk your way up. Every fewer $100 bill adds another possibility that you might have 2 more 50s. So there's 3 ways here, 4 ways here, 5 ways here. And finally, there's 6 ways. If I don't have any $100 bills, I could have either 0, 2, 4, 6, 8, or 10 $50 bills. But I can't have any odd number of $50 bills, and I certainly can't have 12 or more. So I just have to add up these numbers. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. All right, we're gonna remove the zeros of this polynomial, and on how many of the remaining intervals is the polynomial positive. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And yeah, the polynomial equals 0 at each of these points, and it will either change signs or not, depending on if the multiplicity is odd or even. If the multiplicity of the root is even, then we don't change signs. So what happens if x is bigger than 10? Then every factor is positive, so the polynomial is positive there. And so I'm going to not change signs at the 10, but I will change signs at the 9. And I won't change signs at the 8, and so we'll have this pattern. I'll change signs every other crossing. And so this is 1, and so I'll change signs. And yeah, if x is less than 1, every factor is negative, and I have a total of 55 factors. So okay. So how many intervals is p positive? 1, 2, 3, 4, 5, 6. What's the area of the region defined by this inequality? So we need to get a handle on this function. It appears once with x and once with y. So let's think about it this way. Absolute value x will give me this V shape. Moving it down 1 would take the vertex down to the point 0, -1. And then the absolute value here will flip that back up. So I'm going to have a graph that looks something like this. And I'm adding together 2 positive things, and I want to stay less than 1. So I know that for sure x and y both have to be between -2 and 2. And I also know that it's going to be reflective symmetry in both x and y, so I can really just focus on the first quadrant here. So if x is 0, then this term is 1, which means that the second term has to be 0. So if x is 0, then the only possibility is that y has to be 1. And now, as x increases from 0, the value of this term decreases with slope 1. And so the potential y values will increase from 1 in both directions at the same rate. And by the time we reach x equals 1, this first term is equal to 0, which means that y can be any value from -2 to 2, or in the first quadrant, just from 0 to 2. And now we're going to have some symmetry going back. And so anything inside of this square is going to satisfy the inequality. What is the area of this square? Well, the side length is √2, so the area is 2, and there's 4 of them. So 2 times 4 is 8. How many ordered pairs of integers satisfy this equation? Whenever you see something that's close to a perfect square, you want to do something to the equation to make it a perfect square. So I'm going to add mn to both sides. And then I see that the left-hand side is m plus n squared. And the right-hand side, if I factor out the mn, is a sum of consecutive integers. M and n are both integers. And so when can a square be a sum of consecutive integers? Well, it's possible that m plus n is 0. And that's the only possibility, because if you take any other pair of consecutive numbers, right, then, you know, like, let's just go through the possibilities. 0 times 1, okay, that's 0. 1 times 2 is 2, that's not a square. 2 times 3 is 6, that's not a square. And as we go on, how should I say? You're not going to have common factors between n and n plus 1 that make it a perfect square. So, okay, so m plus n has to be 0. So m and n have to be of the form k negative k, right? And so 0, 0 definitely works. 1, -1, and a -1, 1 will also work. But if I have any other number, then I'll have 0 on the left and I won't have 0 on the right. So there's only 3 possibilities. What's the least positive integer m, such that this gigantic number is a perfect square? So we should count our prime factors. And we only care if we have an odd number of these prime factors, right? So what we're going to say is that 2 occurs in 2 factorial, but it also occurs in 3, 4, 5, all the way up to 16 factorial. So if I think about the number 2 first, it occurs in, 15 different factorials, right, from 2 up to 16. So that's 2 to an odd number, but 2 to the 14 is a perfect square. So I'm just going to write down the 2. And then 3 occurs in an even number, so I'm not going to worry about that. 4 itself is a perfect square, so I don't care that it has an odd exponent. 5 has an even exponent, right? 5 occurs in every factorial from 5 up to 16. That's 12 total factorials. Every time my number goes up by 1, the number of factorials it is in goes down by 1. 6 occurs in an odd number. 6 I'm going to write as 2 times 3. Again, I'm going to throw out the even powers. 7 has an even already. 8 is 2 cubed, and it also has an odd exponent, so this gives me another 2. 9 is a perfect square already. 10 is 2 times 5, and it will have an odd exponent. 11 has an even exponent. 12 is 3 times 4. Now 4 is a perfect square, but 3 is not, and there's an odd exponent. 13 will have an even exponent. 14 is 2 times 7. 15 will have an even exponent, and 16 is a perfect square. So this is my list of numbers, and now anytime I have the same number twice, that's another perfect square. So 2 times 2, get rid of those. 2 times 2, get rid of those again. 3 times 3, get rid of those again. And my only lonely remainders are a 2, a 5, and a 7. So I can multiply by 2 times 5 times 7 to make a perfect square. 2 times 5 times 7. An upno is an integer, positive integer with at least 2 digits that are strictly increasing. And a downno is strictly decreasing digits. So no repeats, no numbers between 1 and 9. And so we have an example. So we can have a 0 as the last digit of a downno, but we can't have a 0 as the first digit of an upno. So what's the difference between the number of upnos and downnos? Yeah. Well, how many upnos are there? I think that the way to think about it is that if I select any subset of the digits from 1 through 9, if I select any subset of this, then there's exactly one way to make an upno. So there's 2 to the 9 subsets, but I can't have the empty subset, and I can't have a single digit number, so I'll remove those subsets. So that's U. On the other hand, the D, I can select 0 as well. So I have 10 digits that I can select from. So there's 2 to the 10th subsets. Again, I can't have the empty set, and again, I can't have a singleton. Any other subset of the digits 0 through 9 will give me a unique downno. So D is definitely bigger than U. So the difference, D minus U, is going to be 2 to the 10th minus 2 to the 9th. The ones cancel out, and then minus 10 plus 9, so minus 1. And 2 to the 10th minus 2 to the 9 is 512, right? So minus 1 is 511. The rectangular box has edge length A, B, and C. The sum of the lengths of all 12 edges is 13. So that's the sum of each edge will occur 4 times. So that equals 13. The sum of the areas of all 6 faces. So that's AB plus BC plus AC, and there's 2 of each face. It's going to be 11 over 2. And the volume is 1/2. ABC is 1/2. I want to find the length of the longest interior diagonal. Right, so that's going to be the corner to corner diagonal. And so that's going to be square root of A squared plus B squared plus C squared. So if you want to have A squared plus B squared plus C squared, maybe I'll just square this guy, right? So what I'll see is that A plus B plus C quantity squared, which I know is 13 over 4, quantity squared is going to equal the square of the thing I'm looking for plus, and now the cross terms, I'm going to have AB plus BA. So I'm going to have 2AB, I'm going to have 2BC, and I have 2AC. And that's exactly 11/2. So it looks like x squared should equal 169 over 16 minus 11 over 2. 11 over 2 is better known as 88 over 16. So we're going to have 169 minus 88, which means 81 over 16. Take a square root of that. We have an answer. Okay, A, B, and C are positive integers, and we have a fraction addition. So let's check the denominator here, right? So there's 210 is the least common multiple, right? So this makes sense. So we're going to have something like 15a plus 14b equals c. Yeah. And so, which of the following statements is true? GCD of a with 14 is 1. Another way of saying this is that a over 14 does not reduce. Right? GCD of b in 15 is 1, right? So the second fraction does not reduce. So if either of these are true or both is true, then this fraction does not reduce. And so let's see. What if one of them reduces and the other one doesn't? Like if the first fraction reduces, let's say a is 2, then now we're going to have something over 7 plus something over 15. And that's never going to be, that's going to be like something over 105. So c over 210 will always reduce. So if we have like one of these conditions but not the other, if one of the fractions on the left reduces, then the fraction on the right also reduces. So 1 is false. On the other hand, if the fraction on the right does not reduce, then, well, we just said, then, yeah, neither function on the left can reduce. Yeah, if either function on the left reduces, then the fraction on the right also reduces, and vice versa, right? Let's think about 3. GCD of c with 210. So yeah, the fraction on the right does not reduce if and only if neither of these fractions reduce. Well, it looks like it looks like 3 implies 2. If 3 is true, then 2 has to be true, right? Not only is 2 true, then I should say, if 3 is true, then a special case of 2 is true. All right, so A is not correct because 1 is not correct. 3 only can't be correct because 3 implies 2. All right, so it has to be E, I guess. 2 and 3. Sonia the frog chooses a point in the square 6 by 6 square, hops to it at random, then chooses a distance between 0 and 1, and then a direction, either north, south, east, or west, and hops in that direction. All choices are independent, and what is the probability she lands outside of the square? So what I'm thinking is that if she lands, so we have a 6 by 6 square to begin with. If she's not within 1 of the edge, you know, if she's not within 1 unit of the edge, she can't possibly jump out. And so she has to be, I know, not to scale, diagram not to scale. She has to be somewhere, if I chop the 6 by 6 square up into unit squares, she has to be in one of the unit squares that border. So let's start with that. How many, and then if she's on an edge piece, then her direction has to be south. But if she's on a corner piece, then her direction could be south or west. So I'm going to break that up into 2 cases. All right. If she's on one of the, there's 16 ways out of 36 squares that she might end up on an edge square. And there's 4 ways out of 36 squares that she might end up on a corner square. So we'll pick the position first, and there's 2 cases that we have to think about. Now, if she's on an edge square, she only has 1 direction that she could jump and even possibly go out. Whereas if she's on a corner square, there's 2 edges. And now the question is, if she chooses the correct square and the correct direction, what's the probability that Sonia will actually jump out of the 6 by 6 square? So I'm thinking that there's kind of 2 independent numbers here. One number is jump distance, and the other is distance from edge. And both of these are numbers between 0 and 1 that are uniform and random. And so if she's going to jump out of the square, x, the x number jump distance has to be bigger than the y number. In other words, thinking about probability as an area, the probability is 1/2. So once we know what square we're in and what direction we're hopping, if we have any chance at all to hop out, it's going to happen half the time. And that's the same for both of the possible directions if we're in a corner square. Okay, so I guess this is the answer. Let's add them up. This is going to be 16 over 8 is 2, 2 over 36, 2 over 36, and then we'll keep it in 36 because this is going to be 1 over 36. So 3 over 36 is 1 over 12. Four congruent semicircles are drawn on the surface of a sphere, radius 2, creating a closed curve that divides the surface into two congruent regions. And the length of the curve is what we're after here. All right, so I'm looking at this like point to point of where like one semicircle ends and the other one begins. Right? If I connect all of these, if it's congruent, if it's two congruent shapes, then each of these blue arcs has to be a quarter of the way around the circle. So what I'm going to do is I'll change my angle of perspective. So this is the outline of the sphere, and there's going to be some, and so this the arc that we're looking for is it's not a line of longitude, right? It's going to be some like line of latitude if I orient the sphere correctly. And it'll be something like this. And I'll complete the semicircle to make it a full circle. So what's going on here? Well, we've got the sphere is radius 2. The angle that diameter points make, that these dotted points make, is 90 degrees with the center of the sphere. So therefore, the radius of this guy, the radius of this one of 4 arcs that I'm looking at, is going to be 2 over root 2 equals root 2. And therefore, the length of the semicircle is going to be pi times root 2. And there's 4 such arcs. So that times 4. So I'm supposed to put my entire number inside the square root. So I guess it'll be pi times the square root of 32. N equals 32. Okay, I wonder how the time is going. I think that we are on a very good pace. 2023 balls are randomly placed into one of 3 bins. I'll assume each placement is random. Which of the following is closest to the probability that each of the bins will contain an odd number of balls? Is closest to is an interesting phrase on the AMC. It means that none of these numbers is probably exact. I'm gonna think about it this way, and if we have time, maybe we'll come back and double check. But if we have an odd total number of balls, then it's possible that there's an odd. This is O for odd. It's possible that there's an odd number of balls in each of the 3 bins. It's also possible that we have 2 even bins and 1 odd bin, and this could happen 3 ways, right? But we can't have just 1 even bin, right, and 2 odd bins, because then that would be an even total number of balls. And obviously we can't have 3 even bins either. And so if I'm placing the balls randomly, I'll have one of these 4 circumstances. And so I'm tempted to pick 1/4 just based on that. I can also think that if just 1 ball was in a different spot, I can transition from any one of, like there's 6 ways to pick, there's 6 ways to pick one jar to take a ball out of and another jar to put the ball into. And if I do that, right, I can if I pick like these two jars and switch one ball from one to the other, I'll go from this case to this case. Whereas if I pick, you know, these two jars and switch one ball, I go from this case to this case. So I think that I can, with just one ball change, transition from any one of these positions into configurations into any other of these even odd configurations. And I can do that in an equal number of ways. So I'm pretty sure that the answer should be 1/4. But again, that doesn't sound precise. Okay. How many distinct values of x satisfy this equation? Sorry, my pen is malfunctioning a little bit. So I think what I'm going to do is I'm going to graph, and I'm going to try and solve this by graphing. Right, so I have a greatest integer less than x quantity squared, and then it's going to equal, it's going to intersect a line. So what's going to happen here? Right, if x is between -1 and 1, it's going to round down. If x is between 0 and 1, it's going to round it down to 0. And then when I square it, right, it'll still be 0. If x is between 1 and 2, I'll round down to 1, I square it, and I get 1. If it's between 2 and 3, I'll get 4. So this is 2, 4. And then I'm going to go up to the previous problem here. It'll go from 3, 9, right? And then it'll be, so not to scale here, it'll be 4, 16. All right, that's enough for now. And then it'll be similar on the other side, right? It'll be like this, something like that. I'm not worried about negative x's, because if x is negative, I'll never have an intersection. So let's draw the line now, different color for the line. So it starts at -2 as a y-intercept, and the slope is 3. So if x is 3, I'll get 1. I'll go right through this point. If x is 2, I'll get 4. That's right through this point. 3 will give me 6. Sorry, 3 will give me 7. So this is 3, 7 there. So I'm below. 4 will give me 10. So I'm way below there. 5 will give me 13. So I'm below the open endpoint there. And if I start drawing the line, I'll get one intersection there. These two endpoints that I already knew about. I'll get an intersection here, somewhere on this line at height 4. And then, not to scale, this is still a straight line. And then the squared greatest integer is going to grow much faster than the line, so I'm not going to get any more solutions. But I have 1, 2, 3, 4 solutions. An arithmetic sequence of positive integers has at least 3 terms. The initial term A has an initial term which is A, and the common difference D is bigger than 1. So it has to be bigger than or equal to 2. Carl wrote down all the terms except for one term, which was off by 1. He added them up to 222. So what is A plus D plus N? We don't have too much to go on here. Let's just write down what they are. So it's A, and then A plus D, and then A plus 2D, and finally A plus N minus 1D, right? N total terms. And so the last one's like this. So if I add these all up, I'm going to have first term plus last term is 2A plus N minus 1D. So that times the number of terms and then divided by 2. And that should equal either 221 or 223. Not quite sure yet. All right, so let me, these questions are getting too long for just giving the answer right on the test, right? So let's rewrite this. We have A plus, distribute your N, with NA plus N times N minus 1 D over 2 equals either 221 or 223. And so we have a common factor of N. So let's divide off that N. This is probably how we're going to have to do this. And we're going to have to, so everything's an integer, right? So let's see, is it possible that N is even and everything's a half integer? Could be possible. Seems unlikely. Anyway, if I multiply everything by 2, then I can see N has to be bigger than 3. So N doesn't divide 2. So N has to divide one of these two numbers. So let's figure out the factors here. 3, 5, 7, no, 11, no, 13, yes. So this number is 13 times 17. This one, 3, 5, 7, 11, no, 13, no, and 17 squared is bigger than this number. So this is a prime number. So I'm going to be pretty confident that this one's not possible. If the sum was actually 223, then I'd have to have 223 numbers, but each number is bigger than 1, and well, I mean, the first number might equal 1, but every other number is bigger than 3, so this is not possible. So N is either 13 or 17, and now let's think about the possibilities. If N is 13, then N minus 1 is 12, and so we'll have A plus 6D would have to equal 17. D is bigger than 1, and A is positive. So D can't be 3, can't be 1, so D has to be 2. D has to be 2, and that would make A 5. And that would satisfy all my conditions, and I'd have 13 plus 5 plus 2 is 20. And now, just for fun, I'm going to check what if N equals 17. If N equals 17, then now N minus 1 is 16, and so I end up with A plus 8D equals 13. And now this can't work, because if D equals 2, then I'm already too big, and D is supposed to be bigger than 1. Okay, so I got lucky by testing N equals 13 first. It have to be one of those two. All right, so we have to form a region in the plane points that look like this, where U, V, and W are between 0 and 1. So I think what I'm going to do is I'll figure out what happens when W is 0 and U and V are anything, and then I'll figure out what happens when W is 1, and it'll be just like all the line segments joining the corresponding points in those two regions. So I'm going to do this problem down here, and then I'll have to go to a different page, a different sheet of paper for 25. Okay, so what points do we have? So if U, V, and W are all 0, we just get 0, 0. That's good. If U is 1, then we get 2, 0. If U is 0 and V is 1, we get 0, 1. And then if U and V are both 1, we'll get 2, 1. And as U and V range between 0 and 1, we'll get this entire rectangle. And now, if W is 1, we're going to take each point in this rectangle and translate by -3, 4. I'm going to go from 0, 0 to -3, 4. And then I'll take this point and translate it to 1 up from that. And I'll take this point and translate it to 2 to the left of that. And I'll take this point and translate it to somewhere over there, 1 down from there. And so every line segment connecting points in these corresponding rectangles is going to be possible. So in the end, it looks like I'm making a 3D drawing. I'm not. I'm drawing a region in the plane. And I can already see the length of all the boundaries. Yeah, the length of this diagonal boundary is 3, 4, 5 right triangle. So that length is 5. And so that length is also 5. And that length is 2, and that length is 1. So let's add them up. 5, 6, 8, 13, 14, 16. Okay, last problem. I'm gonna pause the recording for a second. Okay, for problem 25, we have a regular pentagon with a given area, and then we're folding each vertex to the center to create a smaller pentagon. And I want to know the area of the new pentagon. So I paused the video so I could draw, because it's hard for me to draw and talk at the same time. So I wrote out the solution first. So here's what we have. The given pentagon is in black here. I'm gonna just want to be able to see what I have. So the given pentagon is in black. Now what I'm going to do is I'm going to fold each vertex to the center point here, and then I'm going to have a crease that is the perpendicular bisector of the line that goes from vertex to center. So the dotted line is one edge of my folded pentagon, and then this other dotted line is another. And so what do we know about a pentagon? Well, if I draw all 5 of these, then the central angle is 360 over 5 is 72 degrees. And so the total area of the large pentagon, which is 1 plus square root of 5, is going to be 5 of these triangles. And each triangle has an area 1/2 the length of the 2 legs, which are the same. So 2x squared times the sine of the angle between them, times sine of 72 degrees. Now, if I want to calculate the distance from center to vertex of the smaller triangle, right? I just have a little right triangle here. So so x over y should be cosine of 36 degrees. So y is x over cosine 36. And now the area of the small pentagon, right, the solution to the problem, is I've now got 5 triangles. It's the same formula, but now my length, instead of 2x, my length is okay, so there's a small error here. My length should be y, not 2y. I don't want this 2 over here. Right, it should be 1/2 times y squared times the sine of 72. Okay. So what I'm going to do here is I'm going to see that I almost have the number. I almost have the number that I know, right? 5 times 1/2 times 2x squared. Now I want that 2 back, but I'm going to have to divide by 4 to get it back. So 1/2 times 5 times 2x squared times the sine 72 is 1 plus root 5. And what do I have left over? I have the divided by 4 times cosine of 36 degrees squared. Now, now I'm going to erase this because it's wrong from this point, but we can do a quick adjustment. Always check your work for these kinds of small mistakes if you have time. Now the cosine of 36 degrees is 1 plus root 5 over 4. And so I'm going to square it. And so one of the root 5s is going to cancel with the numerator. I'm going to have and one of the 4's is going to cancel with this 4. So, oh yeah, so I didn't make a mistake. So I'll have 4 over 1 plus root 5. And now, this is not any of the given answers because they've been simplified. So I'll multiply by the conjugate, and I'll get 1 minus 5 in the denominator, and I'll get 4 minus 4 root 5 in the numerator. And so cancel out the 4's in the -1, and my answer should be root 5 minus 1. And so root 5 minus 1 is answer B. So I'll stick with that answer. Now, the only thing is, what if I don't know the cosine of 36 degrees? If you don't know it, then you have to figure it out. And so here's a way to calculate the cosine of 36 degrees. There's one way to do it with a pentagon drawing, but I think it's a little bit easier if we have this isosceles triangle. So start with the isosceles triangle that has 72 for the base angle. Then, 2 angles of 72 is going to give you 144, and so the vertex here is going to have 36. Now I'm going to bisect one of the base angles, right? Half of 72 is 36. And so I'm going to set up some variables. If 1 is the original length of the long leg, and x is the original length of the base, then now I've got a smaller similar triangle here. So this leg should be x squared. And then the whole length was 1, so this length is 1 minus x squared. But now, diagram not to scale, but I've got another isosceles triangle because both of these angles are 36 degrees. So 1 minus x squared should equal x. So I can solve for x. It's a quadratic. It's a golden ratio type number. And now I can, if I want to find the cosine of 36, I can look at, let's say, this might not be the best triangle to look at, but it doesn't matter. I can look at one of the triangles that I have, and it'll be much better to use the full triangle. So I wrote this down looking at one of the smaller triangles. But anyway, I get an equation with only x, whose value I know, for cosine 36. I jumped to the answer because I already know the answer. But if you wanted to do it better, you should use the full triangle with the vertex angle and say x squared is 1 squared plus 1 squared minus 2 times 1 times 1 times cosine 36 degrees. And this will be, so cosine 36 degrees will equal, I guess, 1 minus x squared over 2. And we can calculate x squared pretty easily, and it'll give us the correct value. Okay, so yeah, last question was maybe the hardest on this one, especially depending on whether you might have another solution that can avoid knowing the cosine of 36 degrees, but if so, drop it in the comments below. So that was the 10B. I will post this video as soon as it is legal.